Good morning, everyone. So we're going to pick back up at the sort of the very last section of naming. Then we're going to do talk a little bit of a summary of the naming we talked about on Wednesday. We're going to then do kind of a couple of review naming questions together. We have a sig fig review problem following that. It's one we had skipped from a couple slides back. And then following that, we'll be getting into chapter 3 today. So probably the last section of naming that we didn't get to on Wednesday is probably actually the easiest category of naming. It's the naming system for binary molecular compounds. And so this is a binary compound is a compound that has only two elements. And we're going to specifically be naming just the molecular compound version of these binary compounds. Like a compound like NaCl or CaCl2, these are technically binary compounds as well, but they're not binary molecular compounds. So these are ionic compounds. So we name those for the cation and anion nomenclature system we outlined last time. So when we're naming ionic compounds, we're calling that sodium chloride, calcium chloride. We're not switching the name here with this new system we're going to see for the last set of compounds that are common. These are still on the side of, again, molecular compounds. So the naming system is for things like CO2. We have a molecule like that exists between carbon and oxygen. That's a molecular compound. Molecular compounds, again, remember, non-metallic elements are our molecular compounds. Another compound common for carbon and oxygen is CO. I guarantee you we all know the name of these two molecules here, because we all know, I would hope, that this is carbon dioxide, and that this one's carbon monoxide. And so we're using the mono in front because there's one oxygen. We're using di in front because there's two oxygens. It turns out that those names that we probably, and I would imagine we already knew coming in the door, are exemplary of the rules for this category of nomenclature. So the way we name molecules that are binary molecular compounds is we name the element that's either to the leftmost on the periodic table, but it's almost always going to be the first element we write in the formula. So the carbon's written first, so we name that element first. And so, and carbon being to the left is why it's written first. That's why it's not O2C or OC for carbon monoxide. So we write that leftmost element first. Again, if you're going name to formula, formula to name, this is really easy to tell because we'll give you the formula and just ask the name, or we'll give you the name and ask for the formula. So the first name of the element in the formula is the first atom you would write. And so carbon for carbon dioxide. And then the second element takes the IDE ending of the element. So we change oxygen to oxide. If we had chlorine, we'd change it to chloride. And then we're going to use the prefixes that we had used for naming alkanes for the hydrocarbons last time. We were using the penta, hexa, hepta, octa, nona, deca for naming C5 to C10 hydrocarbons. So here we're just picking up the mono, di, tri, tetra for 1, verse 2, verse 3, verse 4 of those atoms in the formula. And the only then exception or piece of the nomenclature system is for the first element, we don't use mono, but we would use whatever the prefix is if there were more than one of that atom in the formula. So we don't call it monocarbon monoxide, it's just carbon monoxide for CO. And so if we look at CCl4 with this system, very simple, right? It's just carbon. And then there's 4, the next element, so it's tetra. And then it's chlorine, but we change it to ide, so it'd be tetrachloride. So just the IDE ending on the second element, the element name of the first element written goes first, and the second element given goes second, and we're just, again, using the prefixes to indicate quantity. If we have 2 of the first element, we, of course, use the dinitrogen first. We only neglect the mono if there's 1 of the first element. There's a bit of a nuance between monooxide versus monoxide. We tend to shorten double vowels. Again, we don't have spelling for this part of the test. Don't worry about the little nuanced details of small little spelling conventions like monoxide versus monooxide. We also have things like, we'll see here for P2O5 is diphosphorus. And then you either call it pentaoxide or pentoxide, but you're trying to indicate 5 with pent, so penta, and then oxide. I think it's fine for this case. Like if you said this in practice, we'd call it pentoxide, but if you just want to make sure to see it's penta for 5 and then oxide, we'd call it pentaoxide and not worry about those little nuanced spelling details. And then the last molecule is kind of a trick, right? So the CrO3 goes back to being an ionic compound, so it's not named chromium trioxide like binary molecular compounds would be named. This just gets named with the system from, we have to have a 6+ chromium, oxygen's a 2- ion, there's 3 of them, 6-, 6+, that's how we get this as a 6+. So this would be properly named for the ionic compound nomenclature system as chromium, Roman numeral 6, to imply the charge of 6+, and then oxide. So just making sure we see ionic compounds still named for that category.
So when we're looking at examples of compounds, how are we supposed to tell whether it's an inorganic or an ionic? Is it just based
Yeah. So the question is when you look at a molecule, how can you classify it? I think it just comes down to first, do you see a metal atom? And so kind of spotting metals from nonmetals would be the first thing. So if I'm looking at a formula for say C2H6, and so for this one here, I'm like, is there a metal present? There's no metal, so it can't be an ionic compound. If I did see a metal, there'd have to be a non-metal, like Na2, SO4 for sodium sulfate, something like that. So metals, nonmetals, ionic compounds. So my next thought would be, does it fit into the category of an acid? So if it's an acid, I would recognize some underlying anion. So if I saw HNO3, I would recognize nitrate ion with H+ added, so this would fit the category of acid. This molecule here, I don't see an underlying ion, so it's not an acid. And then the next thing might be, does it fit the category of hydrocarbon? And it does, so this is ethane. So this is representing the hydrocarbon ethane. So the reason why I like to do the binaries last, I think they're not last in the book if you look the way it presents it, they're a little bit earlier, is to me they're kind of like the catch-all, because I don't want to call this dicarbon hexahydride or whatever, because there's a better name for it. The better name is it's a hydrocarbon that's just representative of having 2 carbons saturated with hydrogen that we call ethane. And so it's kind of like, what's the best category we can put it into? And the categories, and it's kind of summarized. Let me get to this slide here. This slide here is kind of summarizing the categories of naming that we have. We have things like hydrocarbons. So these are carbon with hydrogen only. And so then the only issue here is the count of carbons versus hydrogen goes as the number of carbons. We take that number times 2 plus 2 for hydrogen. Don't let this be too confusing, because if we just have 1 carbon, we're just saturating with 4 H's. And so you could get the 4 hydrogens either just by knowing carbon forms 4 bonds, or by going, well, there's 1 carbon, so the hydrogen has to be 2 times 1 plus 2, so that's another way you get 4. And so just to show this for having, ethane, again, we're just saturating each carbon with 4 total bonds, where we now have a carbon-carbon bond, so these are hydrogens here. And so C2H6, really easy if we just sketch it out, and if we want to use the idea that the 2N plus 2, that would be 2 times 2 plus 2 is also how you could get 6. So to me, what do we want to remember? An equation or just a thought of saturating carbon with 4 H's is how this all works out, or 4 total bonds is how these formulas emerge. If we replace any one of those hydrogens with the hydroxyl group, we get a simple alcohol. And so the simple alcohols would be things like methanol, ethanol, propanol, butanol. If you've seen some OChem, and some of you guys probably have seen a little bit of OChem, you may have seen diols. Diols where you have 2 hydroxyl groups. We're not naming those. If you've also seen organic chemistry, you might have seen how you can know the difference between 1 versus 2 propanol, 1 versus 2 butanol, 1, 2 versus 3 pentanol. We're not worried about the nomenclature system. What we want to know is if we give you something like, let's say the C5. C5 should have 12 hydrogens. How do I know it has 12? Well, either sketch out 5 carbons in a row, add the hydrogens, come up with 12. Think of 2 CH3s on the end, 3 CH2s in the middle is another way. Think of 2 times 5 plus 2, that's a third way. So a lot of ways to get 12, but then if we take one of those away, replace it with a hydroxyl group, that's the alcohol. So the idea would be that this formula here represents pentanol. So then ionic compounds are overall charge neutral compounds, but they're comprised of ions. And so those compounds are named by the cation name followed by the anion name. So here we're trying to recognize metal, non-metal. So we'd be recognizing like NaCl, CaCl2, molecular anions like SO4 2-. We do have one molecular cation that we see here, ammonium. So you see some ammonium salts like NH4 plus paired up, say, with sulfate. So let's say you have ammonium sulfate would be NH4, that has a positive charge, SO4 2-, so I have to have two of the two pluses. So NH4 2 SO4 is ammonium, cation name, sulfate. So our conventions for naming cations are just go alkalized, first group +1. Only charges they form in compounds are +1. The magnesium group only +2. They don't form charges with any other charge. Aluminum only forms a cation with a +3 charge. Nothing else other than +3 for aluminum. Then the transition metal block varies. That's why we use the Roman numeral system for transition metals. So like iron, for example, its most common ions are +2, +3, but I don't want you to memorize that. There's no need to know that just yet. Just know if you need to know the charge of iron, you either get a formula. So we'll see something like FeCl2, so that has to be iron 2+, because we know chloride Cl-. Our anions are atomic ions end in IDE, and that's based on periodic table placement too. So the halogen group -1s, oxygen group -2. Again, just think that the driving force here is heading towards that noble gas configuration. So oxygen adds 2 electrons, has that neon count. Nitrogen gains 3 electrons with a 3-, obtains that same neon count. And so, and then we also have some common ions, so like hydronium. We don't see hydronium too much in nomenclature, H3O+. It's more important to think about that ion as we move into thinking about acids in a couple of different chapters in our book. So we'll return to that later. Ammonium, we see some examples in naming of the ammonium like we just saw. The mercury 1, silver, zinc, lead, those are just the kind of weird ones where you might see silver chloride without the 1 noted, where silver only forms a +1, zinc only forms a +2, lead only commonly forms a +2 charged cation. Not things to be too worried about for the midterm on those 3 ions. And also that goofy mercury 1, where we have 2 mercuries bonded together with the 2+. I doubt you'll see that on the exam, but we'll return to that. We mentioned it. I just want to make sure to include it here. Then we have all those molecular ions like hydroxide ion, acetate ion, the representative oxyanions, the most common count for CO3, 2-, NO3-, SO4, 2-, PO4, 3-, and then ClO3-. Does anybody know that silly phrase to memorize, or the mnemonic that somebody came up with? It's like Nick the Camel ate a clam supper in Phoenix. Has anybody ever heard that before? And so the whole thing there is like, if this is almost harder to remember than nitrates NO3-. So the whole idea here is Nick, the camel, if we start this, is for nitrate is NO3, the number of consonants gives you the 3 oxygens, and the number of vowels gives you the charge. And then so for carbonate, it's 3 oxygens because there's 3 consonants, and then 2 vowels gives you the charge. The silliest thing I've ever heard. A student told me this once, and I'm like, it'd just be easier to remember CO3 2- than Nick the Camel ate the clam. The clam is, and I also then said, well, how do you know clam was for chlorine and camel was for carbon? But so this is for the chlorine, so that's ClO3-. Supper has 4 consonants, 2 vowels, that's SO4 2-, and Phoenix is the cool word that has 4 consonants for PO4 3-, and then 3- for the charge. Again, you can Google that if you want. I'll just, just if you start Googling that, it'll come up. It's one of those silly mnemonics that people remember to remember things. I still remember the keep planet clear of, what is that, flying order systems or something for Kingdom Phylum class. Do you guys remember that one too? Yeah, wrong room for that topic. But anyways, so that's kind of our basic representative oxyanions, and then we're just learning the system for adding an O to that formula goes per, take an O away, change the 8 to ite. If you take a second O away from the formula, keeping the charge the same, goes hypoite. So chlorate ClO3-, change that 3 down to just 1 O, that's hypochlorite. So just knowing that system is for our anions. Acids are pretty straightforward. As long as you know how to name the underlying ion, you just go ide to ic acid, or hydroic acid. The ates go to just the ic acid, and then ites go to us acid. We'll see a few examples of those in a moment, just to go through a quick review, and then our binaries are everything else that's left over. So it's trying to categorize, when you look at a compound, think, is it ionic, is it molecular, is it best described as a binary molecular hydrocarbon, is it an alcohol? Those are the thoughts you can have when we're naming molecules. Okay, so for this slide here, why don't we put like a 2-minute timer and see how many of these you guys can name in 2 minutes, and after about 2 minutes, I'll just go through all of them and talk about them briefly. See if you can get them all. Does anybody think they got them all, just out of curiosity? Okay, let's see. Anybody close? Anybody far away? Okay, well, let's think categories as we go along. So when I'm looking at these, it's making sure we get the categories. So that's an ionic compound, because I see metal with some collection of other things. So that's going to be sodium plus. And then I'm thinking hypochlorite goes off of chlorate. And so that's ClO3 with the minus. And so hypo with the ite means I've lost 2 of those O's down to 1. So that would be NaClO minus, and then just pairing up 1 plus to 1 minus, so NaClO. Iron 3 acetate, also an ionic compound, because I see metal cation. I see some sort of non-metallic collection of atoms for acetate ion. So I have Fe3 plus. The transition metals are nice because they tell us the charge. And then we just have to think about the charge of acetate, the formula of acetate. It's 2 ways of expressing the formula. Probably the most common way, especially at this point in the class, is C2H3O2. This is the formula with a minus charge for acetate. And I'm going to need 3 of the minuses to pair up with the 3 plus, because I got to go overall charge neutral. So I just got to balance the minus with the plus. So 3 minuses for the 1, 3 plus. So Fe, and I just try to show that the formula wouldn't have the charges expressed in it, so I'm just lassoing out the actual atoms here. So Fe, C2H3O2, 3. And then we could also write this CH3COO minus. I think this makes a little more sense once we see molecular structure. So that's another way of expressing the formula. So we could have written it this way as well. I think that looks a little bit sillier. I think when you're expressing a formula for a salt, C2H3O2 makes a little more sense. Now, acids are easy to name. The category of, at least, if you see the name written out, because you know it's an acid with the word acid afterward. So we know this is in the acid nomenclature system. And then perchloric is based off of perchlorate. And so that would be ClO4 minus, because again, chlorate ClO3, add an O goes to per. So perchlorate is ClO4 minus. Neutralize with H pluses, just takes 1 for the 1 minus, gives HClO4. So that's perchloric acid. Also a very nasty compound I mentioned before. Don't feel like just because you know the name of a compound means it's safe to work with. That's a very hazardous compound. So things like hydrofluoric acid, perchloric acid, some of the nastiest compounds to work with. So if you're ever working with this in the lab, make sure you know what you're doing. Nitric acid, also an acid obviously, but based off of nitrate because of the ic acid. So NO3 minus is nitrate. 8s go to ic acid when they're neutralized with H plus. And again, 1 plus, 1 minus neutralizes out as HNO3. If we had something like H2SO3, that's an acid. I can spot the acids with usually H out in front and then some underlying ion I know how to name. SO3 2 minus is based off of SO4 2 minus, which is sulfate. So this would be sulfite. And so SO3 2 minus is sulfite. We neutralize this with 2 hydrogens, so H hydrogens plus, right? That's why I need 2 of them. So H2SO3 would be sulfurous acid, so sulfurous acid. To me, the only confusing part is you add the root name longer for sulfur, so you call it sulfate instead of sulfurate. So sometimes you, like I mentioned, sometimes you change how long of a hyphenation you use on an element name. Here, we're going sulfurous as opposed to, say, sulfus. But if you thought this should be sulfus acid, I think you get the system. So I wouldn't worry about, again, the spelling. The spelling conventions are nuanced. So this would be sulfurous. So the thing we're picking up is root name of the element, OUS acid, based off of the ite. H2S, if we're naming this as an acid, it actually really isn't so acidic, so we tend not to always name it as an acid. It's a gas, it's the smell of rotten egg. So H2S is usually called just hydrogen sulfide, is its more common name, just that it's tend to be used in common speak. But if we want to name it like it's an acid, though, with our acid nomenclature system, that just means we're kind of thinking about sulfide. And so if this is sulfide, and we change that to its acid form or neutralize it with acid, so 2 of them, that goes to hydro, because the ides go to hydro, then the root name, so hydrosulfuric acid. So hydro, and then keeping the ic acid name. We don't want to call this sulfuric acid because that's H2SO4. So we want to make sure that hydrosulfuric acid has a different formula than sulfuric acid. N2O4, now again, this isn't a hydrocarbon, it's not CNH, it's not an acid, doesn't have H in it, doesn't have a metal, so it's not an IC. So this is that binary molecular compound. So dinitrogen, tetra, or tetroxide. We'll just keep it with tetraoxide. So then our hydrocarbon, and then hexane, so C6, hexa, that's why it's 6. And then how many hydrogens? Well, if we only had H12, the N carbons wouldn't have enough hydrogens to saturate them. That's why we got to go 14. So either 6 times 2 plus 2 for 14, or sketch out the carbons 6 in a row and just add the hydrogens, and you'll get the 14. Decanol, the OL ending tells us it's an alcohol. It's an alcohol of a hydrocarbon. That's all we know how to name, are basic, simple alcohols of our straight chain or our simple hydrocarbons. So we'd go to decane. So think about decane, or just decane. So C10H 2 times 10 plus 2 would be 22, or sketch it out. And so then for decanol, what we want to do is take one of those hydrogens away to go to 21, and then add the hydroxyl group in its place. So we could have called it C10H22O, but here we're trying to imply by writing the OH group that it has that hydroxyl group. So I just always like ending kind of the nomenclature topic with the goofy names. You can give water with the different systems. It kind of goes through systematically how you might name water a few different ways. And sometimes people use these names colloquially just to be funny. So like we've probably all heard dihydrogen monoxide, but that just fits the binary nomenclature system. So dihydrogen monoxide is the name you would give water if you wanted to name it like it were a binary compound. You could think about how like the oxide ion, or the sulfide ion example we just did, it's kind of the acid of oxide ion, even though water isn't particularly acidic. But we might think of calling this hydroxylic acid. We probably would abbreviate it hydroxylic acid and get rid of the double O's, but whatever. If we want to name the acid of hydroxide ion, so if you have the hydroxide ion, what if you just think of this as being the acid to make H2O? So maybe you would call that hydroxylic acid. I also like to think of how, remember how we were naming like hydrogen carbonate was an H plus added onto carbonate ion? Well, hydroxide is really H plus added onto oxide ion, and it's kind of interesting that you would name it hydrogen oxide, shorten it to hydroxide. So the name hydroxide is actually kind of coming from that same system that we were naming hydrogen carbonate. So like hydrocarbonate, if we shorten it, would be a similar name. And then we can also think, well, we're just kind of making an alcohol of hydrogen. We're just getting rid of an H and replacing it with a hydroxyl group. It's kind of what water is. And that would be hydrogen in its alcohol form, maybe hydrogenol. So maybe go around talking about how we should turn to a hydrogenol fuel planet instead of using fossil fuels. People will be like, hydrogenol, what's that? Water. All right, so one sig fig question here. Let's go ahead and do this together. We can do this as the lecture survey 7. Today's password to get in is mole. So hopefully we'll get into the mole here in a little bit. Take like a minute or two to think about the sig figs on this one. And there's the second question we're not going to get to, so you can skip the second question for today. And then the third question is asking what topic you're kind of thinking is the hardest or you might want to review the most before midterm 1. So if you want to think about that for a minute too, feel free. But we'll pause for about 2 minutes here. right, so we'll take a look here. I'm just kind of watching some of the answers come in. We're like 80% towards answer C, and that is the right answer here. And so the way the sig figs kind of work is our problem here, we want to do the multiplication step and think about its sig figs first. And so if I do that step, I get 0.00819, and then that should only have 2 sig figs because I have 2 times 3, so I would round that. If I'm giving that as the only answer, it would be 0.0082. We could keep the 9 around, we could round, don't let that confuse you. If you want to round up, feel free. And then the next step, we have to add the 1.002, and so both of these values, or excuse me, the 2 is good to the thousands placeholder. The 00819 is good to the ones placeholder. The greater value placeholder is this 2 value. And so that's where we have to round. We have to round to that 3rd decimal place. And so when I get my answer, I'd round it to 1.010 with all 4 digits, well, with 4 digits being significant in the result. So what we have to remember, multiplication, division, we count sig figs, round accordingly based on the number of sig figs. So this would get rounded to 2 sig figs. But when we add and subtract, it's not about sig figs, it's about the placeholders. So it's about this ending in the 4th decimal place, this value here ending in the 3rd decimal place. We round to that 3rd decimal place to 1.010 with 4 total sig figs. Okay, bunch of reviews again on the daily quizzes. There'll be some on the combined practice exams. Those should post soon. I just sent an announcement about office hours this week. I will hold an office hour today after lecture till about 12:15 in 2047 McPherson. So just head over there after class if you're interested today. Same thing Friday after class, same thing Monday after class, adding those office hours before the exam. So check out the announcement I just sent out before lecture about that information. Some combined practice midterms should be going up relatively soon, probably tomorrow or the next day, for getting ready for the midterm. Those are kind of like full-length practice exams. And there's, of course, the daily quizzes you can use to help prepare. So with that, that kind of wraps up chapters 1 and 2. We got to get through about section 5 and chapter 3. If you ask me, the hard part of chapter 3 are section 6 and 7. We'll talk about after the midterm. I don't think they're that hard, though. But a lot of questions, a lot of material, a lot more time's needed for those final 2 sections. I think we will get through the first 5 sections, probably through middle to a little bit past middle of lecture on Friday, so we can start doing some review problems after that on Friday. So I like to spend, the rest of lecture Friday, also next Monday, working on review problems. I've already thrown a review packet up. I'll actually put some answers up if you want to work on that ahead of time, that's fine. But there's a packet of review problems we'll work on in lecture, posted in the lecture slides area. Okay, so for midterm 1, we're getting through section 5. What is chapter 3 about, though? So chapter 3 is on the topic of chemical reactions. The first 2 sections just kind of lay out what is being implied by a chemical reaction, how we can include physical states in the reaction, think a little bit about that. We talk briefly about a couple of different categories of chemical reactions that we can think of to get some basic types of reactions that tend to occur. We'll talk about 3 different types of reactions in the next couple of slides. Just real basic reactions. In the next chapter, we'll get into a few more complicated reactions like precipitation reactions, acid-base reactions, but those are coming in chapter 4. The reactions in this chapter will be like combustion reactions and then a couple other simple reactions. And then the remaining part for midterm 1 will be looking at formulas. So getting into the mole unit, thinking about molar mass, and then thinking about how we determine formulas from experimental experiments. So we'll be discussing those details through section 5. There's even a problem in section 5. We won't cover it all this semester. We'll talk about what it is. It's kind of a long problem, so I'll kind of show you what it looks like at the very end of our coverage here through section 5. And then after midterm 2, we'll get into section 6 and 7, which is on the topic of stoichiometry, if you remember that word. That's the quantifying aspects of chemical reactions. That's the limiting versus excess reactant type problems. That's how much yield do you get? What's the percent yield? You might recall some of those problems. That's after midterm 2. Okay, so real basic here would be thinking of chemical reactions. We had exploded a balloon. If you were here, there's a video of it up online of exploding a balloon with H2 and O2 in it. Now, H2 and O2 were the reactants in that reaction, and they were gaseous in a balloon, so they're gases. Sometimes in a reaction, you can predict or know the state of the substance. Sometimes you may not know easily the physical state, but the key would be in any chemical reaction, the reactants and products have some physical state that you may or may not predict, but may be written in the formulas, either gas for gaseous, solid for solid, and L for liquid. But here we're forming water. When we combusted the balloon, we were just making that stable molecule water. It was probably not raining. We probably didn't see a puddle form afterwards, so probably flying away in the heat as gaseous water molecules. Again, not always easy to predict, or not always the point that you can predict the state, but that we tend to write the physical state of the substances in a chemical reaction as gas, liquid, or solid. And then from here, we have to think about this being, of course, the before. This is really basic, but this is what's present before the reaction. This is present after the reaction. So we have to think about mass balance of not creating or destroying matter. As written, I've kind of lost an O atom. The easy way I can solve this problem would be to, of course, do 2 in front of H2, do a 2 in front of water. So, of course, that gives me 4 hydrogens on both sides, and give me 2 O's on both sides. So we got to balance the number of atoms on the left side versus the right side so we're not creating or destroying matter in reaction. We're just changing the nature of the bonding between hydrogen and oxygen. So we're starting from the idea of having 2 molecules of hydrogen. That's represented by the 2. So the thing sometimes, if you haven't had chemistry in a while, you're thinking, why didn't we just write H4? Well, H4 would represent a molecule with 4 hydrogens connected together. We don't have that. We have 2 distinct molecules of H2 separate from each other. We have a molecule of O2, and then those bonds must break somehow and then reform with an oxygen wedged between the 2 hydrogens. So water's forming here. We get one of them, and then we get the other. So the coefficients we're using here to balance the reactants and products, the number of atoms on both sides. We can't change the formulas, right, because that's changing the nature of those molecules. H2 has 2 hydrogens connected. We can't just change that to H4 because 4 hydrogens don't just bond together in that nature. And so this is just implying that we have this before, and then after the reaction we would have this collection. So we have the H2 and the O2 lost after the reaction completes. And then maybe we have the idea that generally we don't just have 2, like when we combusted the balloon, there are way more than 2 molecules of hydrogen, way more than 1 molecule of O2. We probably had millions upon millions of atoms, and we start to think about things in the mole quantity, more like an Avogadro's number. So we probably had on the order of like 10 to the 22 molecules of H, and probably about half of that in terms of the number of O. And so as you start to think about the actual collection of atoms that you combust, way, way bigger amounts than what we're portraying here, what we're going to eventually get to is the idea of moles. And once we get there, and we can say it here, then you could also look at it as a reaction as being the mole units. That we can see that, or hopefully just lay the groundwork, that 2 moles of H2 will react with 1 mole of O2, the same ratio as the molecule. So if it's 2 molecules of H2 to 1 molecule of O2, it would be 2 moles of H2, 1 mole of O2 combining to form 2 moles of water. And we just have to learn moles of conversion factor. And we're not going to get into that just yet. We'll maybe get into it by the end of lecture today, but that'll be kind of the next, or a big topic in this chapter, is try to understand what is the mole, how can we use it in problem solving, how can we understand what it means. Let's then talk about the little bit of patterns of reactivity we can understand. So some basic types of reactions that take place are simple combination reactions. That's just where we have 2 elements combining to form a single product. And so sodium and chlorine do this. In fact, our metals and non-metal elements tend to do this to form ionic compounds. So this is the basic reaction that forms most of our ionic compounds. And so to balance out the chlorines, we need to do 2 NaCl's. So then we need to do 2 sodiums. So note that even though we have two molecules, or probably molecules not a good word for an ionic compound, but we have like 2 units of NaCl or 2 moles of NaCl forming, we don't need it to be 1. We can form more than 1. We just have to form a single product. So a combination is where we have 2 or more reactants combining to form a single substance on the product side. We can predict the products for some of these reactions if we know the charge states common for like aluminum, being Al plus as it forms its, Al3 plus as it forms its common ion of 3 plus. Oxygen's common ion would be O2 minus. And so then this formula here would just be Al2O3. And so that would be our product, Al2O3. To balance this out, 3 versus 2 oxygens. So why don't I put a 2 in front of Al2O3? That's 6 O's total. So then 3 O2s. If I didn't do the 2 versus the 3 here, I would have to use a fraction. I tend not to want to use fractions in a balanced reaction. So in a properly balanced reaction, we generally would not have fractions. And so then we then need 4 aluminums. So 4 Al plus 3 O2s give me 4 aluminums and 6 oxygen atoms. on this side of the reaction, we're balancing that out on the product side. Also take note that a reaction that has two uncharged molecules forming and mass balance a uncharged molecule, we have charge balance too. So we can't be creating or destroying electrons either. We can't be creating or destroying charge. So if we start uncharged, we need to end uncharged. If for some reason we started with a net plus on the reactant side, we need to end with a net plus on the product side. So we can't be creating or destroying charge here. So we need mass balance. The atoms need to be balanced. That's pretty easy. And then the charge should be balanced too. And generally, it's pretty easy to balance the reactions you see early on in chapter 3. If you ask me, when I think about high school, the few things I still remember about high school chemistry, I remember balancing the goofiest reactions and some of them being really challenging. I can't think of any reactions we give you to balance that are that hard to balance here in chapter 3. The only time, if you ask me, we get into hard balancing, if you guys happen to remember the topic of balancing redox reactions, that's tricky. That's like a chapter 20 topic in Chem 1220. So if you've seen that and are thinking about that, that's not till well down the road. So the opposite of a combination would, of course, be decomposition. So a single reactant decomposing into two or more reactants is a decomposition reaction. And the only common version of this reaction we tend to talk about are metal carbonates tend to form metal oxides plus CO2. So we're just losing the CO2 off of the carbonate. So we leave behind the O2 minus. So what was CO3 2 minus becomes O2 minus, CO2 flows off of it. And so this happens when we heat the reaction up. Sometimes you see a delta symbol. This just means heat is applied to the reaction, either as a spark or as a constant heat source. This has to be cooked up. So you kind of heat up calcium carbonate, it cleaves off the CO2. This is interestingly a component of making cement. So if you make cement or use cement, you've actually have created CO2 into the atmosphere. So the production of cement leads to the production of CO2. There's a lot of sources of CO2 in the atmosphere that aren't just fossil fuels being burned from automobiles. A lot of different sources. This would be one of them. Cement is, I think, about 5 to 10% of the global human production of CO2 in the atmosphere comes from just cement and building industries. And so anyways, we're just seeing a basic reaction here, decomposition, one thing turning into two. We can predict the products of iron 3 carbonate. I know that's iron 3 carbonate because carbonate's a 2 minus. And then I have to have a 3 plus for the iron. That gives me a 6 plus to balance out the 6 minus. So I can deduce the charge of iron there to be 3 plus. I kind of just took the coefficients backwards. If you remember, we had 3 plus, 2 plus. We switched the coefficients. I just went back up to the charges as well. So that's iron 3 carbonate. We're going to get iron 3 plus oxide. So we're going to get Fe2O3. So we keep all 3 of the oxide ions and we cleave off 3 CO2s here. Not a big detail. This probably isn't a category that we actually expect to have memorized in terms of metal carbonates forming metal oxides, but it's one, if you see one example of a reaction, you can predict the second. So a lot of questions on, a question like this on a test is usually, in a decomposition reaction, some carbonate by name or formula forms some oxide by name or formula, and then write the balanced reaction. So you get some information about the reactants and products, and then you can balance the reaction accordingly. So we're cleaving off the 3 CO2s from the 3 carbonates of this reaction. Okay, so that's decomposition reactions. And then combustion reactions are probably by category the most important reaction on this page. They're the reactions where hydrocarbons are burning in the presence of oxygen, also with a heat supply, generally more as a spark. So just give these a spark, and the reaction, just chain by chain reaction continues itself. And so CH4 reacts with O2 to form CO2 and water. So the common products of a combustion reaction of a hydrocarbon containing CH or even CH and O would be CO2 and water. And so the products of these combustion reactions are CO2 and water. Now, one caveat is if you don't have enough O2, if your intake is blocked on your car and you have your engine running, it could be producing carbon monoxide. So this reaction can actually change its product if there's not enough oxygen. And so this is just kind of a warning that if you're sitting in a car in the cold in the winter and you're cold, you got the heat on, you might want to consider turning your car off or not running it constantly or have a window down, because if for some reason your filter is clogged on your engine intake, or let's say you got into a car accident. This has happened before. A car got in a car accident and it's sitting in a pond and the pond's blocking the oxygen intake from the engine, but for some reason the driver let the engine running. This actually happened in Marysville, Ohio a couple of years ago. 2 passengers died from carbon monoxide poisoning because they're waiting for a tow truck and left the engine running, had no idea that carbon monoxide, it's the odorless gas, so you won't smell it, and then you start to get delirious once you start to have a little bit of it in your system, and then you have a lot in your system and you can't recover from it. It replaces the O2 in your hemoglobin, and the only way to survive is to not have it replace all the hemoglobin and have enough time to have your body produce new hemoglobin. So you kind of have trashed all your hemoglobin in the process. It's a very deadly gas, so you have to be very careful if you have natural gas furnace. If you have automobiles, you have to be careful with the exhaust fumes from those cars. So just kind of a public service announcement that I like to give whenever we talk about this topic. And it's interesting, most reactions, if you run out of a reactant to stop, this reaction will change the nature of the product it makes. If we run out of oxygen, it just changes and says we don't have enough O to make carbon dioxide, you're getting carbon monoxide, and good luck. So, so just be wary of that. But as written, we can balance this reaction to produce CO2 and water. So just 4 hydrogens. So we can put a 2 in front of water to get 4 hydrogens. And then I have 2 plus 4, so I have 4 O's on the product side, so I need 2 O2s. So I didn't leave a lot of room to write the coefficients in, but 2 in front of oxygen, 2 in front of water, 1 CO2, 1 CH4 to balance. We can then predict the products of basically any combustion reaction that has CH or O in it, because we're just going to form CO2 and water. So I'm going to form 3 waters because I have 6 hydrogens. And then I'm going to need 2 CO2s to balance the 2 carbons. And so that gives me 4 plus 3, that's 7 O's. So I have 1 O here, so I need a 3 in front of O2. So a 3 in front of oxygen, just making sure that we see this is a 3. So 3 O2s give me 6, plus the 1 from ethanol, give me 7. So that gives us the proper count here for 2 carbons, whoops. So 2 carbons plus 6 hydrogens plus 7 O's, producing that same count. So 2 carbons, 6 hydrogens, 7 O's on both sides of the reaction. So again, balancing pretty straightforward. Just balance out the number of atoms on the reactant versus product side, and just remember sometimes the book calls these chemical equations. I don't like to call them equations because it's not that the left side equals the right side. It's that the left side turns into the right side by chemical reaction. It's a before and after. To me, it's not an equality. I think the word equation is silly to use. So I think of these as chemical reactions. The book calls them chemical equations, but just think that this is implying what's present before versus after. So we had to have mass and charge balance in our reactions. So for one of the things we might want to know is for a given molecule or compound, can we express its formula weight? So a formula weight would just be the weight of all the atoms in the formula from the periodic table masses that we see. So for C2H2, I could write a formula weight as that being 2 times the mass of carbon. So I just go to the periodic table for carbon, it's 12.011. I usually use for textbook problems 4 sig figs by default. For lab problems, you might have to look more up. But for textbook problems, for exam problems, I think if we use 4 for most elements, we're going to be good and not have sig fig issues and rounding issues. Most students use 2, and that's probably okay. You can probably get away with using 12, but I just kind of have memorized and use them all the time as 4 digits, so I tend to use 4. But anyways, I'm just adding up 2 times carbon, 2 times hydrogen. Hydrogen's 1.008, and so this would go to 26.04, or excuse me, 26.04. If we do that math. What are they always moving up there? So that would be our formula weight of C2H2. Now, C2H2 is a molecular compound, and for molecular compounds, we might want to say, well, what's the molecular weight? The molecular weight's the same thing. So for C2H2, this molecular weight would be the exact same idea and the exact same value as the formula weight. So for a molecular compound, these two are synonymous with each other. So formula weight, molecular weight, no difference between the two for a molecular compound. The only odd part is when you look at an ionic compound that, K and the K plus ions don't really attach to the sulfate ions the way they do in the molecular compounds. So that's not really a molecule. So this would be SO4 2 minus with some sort of charge. We'd have a K plus ion, another K plus ion where they're not actually bonded together covalently. So we don't tend to call these a molecule. Just a little nuanced detail where we would tend to give a formula weight for K2SO4 but not a molecular weight. And so for the formula weight for K2SO4 would be 2 times the mass of potassium, which is 39.10. And again, these units, we can just keep using. The mass are just atomic mass units. Now, we need to connect that to grams per mole. We're going to be getting there soon, but we need to connect that to grams per mole here soon to get the molar masses. But the atomic mass unit is just like the average mass of the atom in that atomic mass unit scale. And so 39.1 AMU for potassium, 1 times 32.06 for sulfur, so 32.06 for sulfur, and then plus 4 times 16.00 for oxygen. So I get 174.26. AMU is the formula weight for K2SO4, and I would probably not say that it has a molecular weight. This is a minor detail, but I just like to think of classifying ionic compounds and treating them a little bit differently and thinking of them a little bit differently. Makes a little bit of the vocabulary tricky because we want to just look at a collection of atoms and call it a molecule, but ionic compounds really aren't a molecule in the same way that C2H2 is. And so like it just starts getting into the thought of K2SO4 is going to be a solid with a bunch of ions. A sample of acetylene probably won't be a solid. It actually is a gas at room temperature, not that you necessarily have to predict that, but you would have 2 carbons connected, hydrogens on either end. A collection of C2H2 would be a bunch of individual molecules that are separate from each other. So that's the idea of molecular compounds, is like you have that formula separate from another formula. Okay, so we have a little bit of time here to start thinking about the mole and Avogadro's number here today. And so what the mole is it represents that Avogadro's number of a thing. So a mole is defined as being 6.02214076 times 10 to the 23, and you would have that number of objects in the thing. So imagine having an Avogadro's number of pennies. That would be 6.02214076 times 10 to the 23 pennies. Hard to picture that many. That would be a huge, tremendous number. So the book gives this example. If you were to circle the equator of the Earth in pennies, how many times could you do it? So could you circle the equator of the Earth in pennies? If you had an Avogadro's number of pennies, and if we start thinking of Avogadro's number, that's the number of atoms that are in a carbon-12 sample that's precisely 12 grams. So if you have 12 grams of carbon, that would have 6.02214076 times 10 to the 23 carbon atoms. 12 grams is about the mass of a sugar packet. So mass of a sugar packet of carbon atoms has that number of atoms. If you have that as pennies instead of carbon atoms, so take that number of pennies, you can circle the equator over 14 or about 14 trillion times. That's just how big that number is. Okay, so here's also how big that number is. I thought about this yesterday. I've never thought about this before. What if you had the actual carbon atom itself? Carbon atom is about 3 angstroms, about 3 times 10 to the minus 10 meters. What if we circle the equator with carbon atom? Could we get there? Could we get the whole way around the equator with a mole of carbon? Not only can we get there 90,000 times. We can circle the equator 90,000 times with the number of carbon atoms in 1 mole and 12 grams of carbon. That's just how big that number is. So the mole to the Avogadro's number, it's just a conversion factor. It's just a simple conversion factor. Another thought that I had is, could you get to the sun with carbon? So if you just stack carbon on top of each other, can you get to the sun and back? Yes, you can, 600 times for just 12 grams of carbon. So you can get to the sun and back just overlaying the atoms on top of each other 600 times. I think that's pretty crazy. But so the way the conversion factor works, so the way you kind of link grams to AMU, is you just say, okay, if we have that many carbon atoms in a 12-gram sample, then we can get the mass per atom very easily. I could say the mass of a single carbon-12 atom is just that 12-gram total divided by that total collection of atoms. And if I do that math real quick, if I do 12 divided by Avogadro's number, and for some reason I'm being really precise here, so I'm including all the digits, just because it'll give me the exact conversion factor, I get that the single atom of carbon is 1.99, and I'll round it here, 993 times 10 to the minus 23. So let me write it here, 1.993 times 10 to the minus 23 grams. So I can calculate the precise mass of that carbon-12 atom. And then what we do with the AMU scale is we say that mass, that this mass here, is just equal to 12 AMU. So that's the connection between AMU and grams. As we say that mass is equal to 12 grams. And so if you divide that number, if you have it on your calculator, that's fine. If I divide the number on my calculator by 12, that gives me the AMU to gram conversion. That 1 AMU is equal to 1.6605 times 10 to the minus 24 grams. If you invert that number, you get Avogadro's number. So you invert that number, you get back to Avogadro's number. So 1 AMU is equal to that small number of grams, but a gram is equal to an Avogadro's number of AMU. So you start with Avogadro's number, you do a couple conversions, define something, you come back to Avogadro's number. Okay, we'll talk about this again. It's good to talk about this twice. This is something really important to talk about twice. Students often don't understand the mole that well. We'll pick back up from this slide, kind of talk about it again on Friday and move on from here. All right, guys, have a great day.